Okay, so welcome back to another video of computational methods, where today we'll continue our thoughts with root solving, and we'll take Newton's method a step further and go off and demonstrate and apply Broyden's method. Okay, for Broyden's method, it's a method which will circumvent the utilization of this expensive inverse function. Remember that taking the inverse of a matrix is rather expensive, and for this Newton algorithm, although it's very simple, every single iteration it will take an inverse. So for very large equations with very many unknowns, that becomes extremely slow. So the benefit with Broyden's method is that Broyden suggested using the Sherman-Morrison formula, which is a mathematical formula used to equate the new inverse of a function after an operation. It is put in the terms of the old inverse. So in reality, you only ever need to use the inverse, that expensive inverse operation, once in theory. We'll see why it does not work in theory later. Okay, so the cusp of Newton's, the cusp of Broyden's method is this here. The new x value is going to be described by this xn minus inverse Jacobian matrix multiplied by f evaluated at xn. So let's go ahead and code out Broyden's method. Okay, so we call this Broyden. What does Broyden need? Broyden needs a function to solve the root of a initial guess and then the Jacobian of the function. It also needs our usual suspects for other arguments. Okay, so we have define. There we go. Okay, so first things first, we go off and do a J inverse. We want to designate our J inverse. You notice that we never use the pure Jacobian, only ever the inverse of the Jacobian. Okay, so that's rather convenient. J inverse is equal to, let's say, the Jacobian we inputted evaluated x naught. Okay, and this will be inside of parentheses, right? And it will be jnp.linalg.inverse. Okay. Next, we want to designate an f naught. F naught equals f evaluated x naught, right? So we are ready to start our algorithm. So for I in range max iterations. Okay, first things first, let's find our new x1. x1 is equal to, and rather than that, let's split it up. x1 is equal to what? You notice it's x, our old x, adjusted by some value. This a value I'll call dx here. So dx equals the negative J inverse matrix multiplied by f1. Okay, you'll see why in a bit. The problem with this method is that we may not always make good progress. So in order to combat that, we need to implement two things. Number one, something called step control, and number two, to reevaluate the Jacobian, because the Jacobian can become corrupted after a certain number of steps. Reevaluate the Jacobian if you're not making ample progress. So how do we define progress? We define progress as the JNP linalg dot norm. So norm being the magnitude. Okay, the magnitude of f1. So the new one. Okay, what is that supposed to be? If we're making progress, we'd like the new values to be of lower magnitude than the old values, right? Such that we're approaching 0. So instead, I'd like to do the opposite. So I'm saying while we're not making good progress, okay? While we're not making good progress, I would like to do the following. I would like to define, let's define some constant alpha. It'll be initially equal to 1, okay? And this is our step. This is the idea of step control. While we're not making good progress, maybe our step is too large. So I'd like to decrease my step. By a certain number. This is completely arbitrary, something like 0.75. Okay, 0.75. Then I check if I also need to check. I don't want my step to be too small. If it becomes too small, so if alpha is smaller than, let's say, 1e to the negative 7, then I'd like to reevaluate my Jacobian. Okay, reevaluate that. Dx is dependent upon the Jacobian inverse, and I designate a new x1 at this point. Okay, so after all is said and done, I almost I believe I keep do I keep that there? I think I don't need an alpha here, but after all is said and done, I'd like to increment I'd like to find my new x matrix by adding it to alpha times dx. Okay, so this is implementing step control. So if we are making good progress, what would I like to do? I'd like to also check if we have a solution yet. So if the norm of the F1 matrix is less than the tolerance, then I'd like to break. So if we're making good progress, but we have not reached the solution yet, what should I do? So we go back to Broyden's method. For the cusp of Broyden's method is that, again, you can approximate the new Jacobian by improving upon the old Jacobian, and that's what this is here. The new Jacobian is equal to the old Jacobian adjusted by some value. Again, he applies the Sherman-Morrison formula to only use the inverse Jacobian of the old function. So we go off and do that. See that it's dependent on delta x and delta f. So that don't overthink that there. So delta x and delta f is equal to what? X1 minus x naught and f1 minus f naught. Okay, easy peasy. Then we go off and calculate our new J inverse. So we update our J inverse. So J inverse equals J inverse plus, okay, plus dx minus J inverse matrix multiplied by f. Let's see, df. Okay, so this whole thing parentheses, and you notice we have this let's see, matrix multiplication x dot, let's see, d I have to be very careful here, dx dot transpose matrix multiplication J inverse. Okay, so this whole thing under a parentheses, all divided by dx transpose of dx matrix multiplied by J inverse, the old J inverse matrix multiplied by what? df. Okay, no transpose. Okay, with our new Jacobian, we like to throw away our old values at this point. Okay, so we say f0, or let's do x0, f0 is equal to f1, or x1, f1. Okay. After all is said and done, if we either break out of our for loop or we reach our maximum iterations, either or, I'd like to return my x1 and f1, my answer. Okay, so let's try this out. Okay, we need an initial guess, so let's do an initial guess is equal to the remember we have to work in Jack's numpy arrays, so let's do 0, 0. We'd expect to see an answer like the Newton's method. Okay, so we'll go off and write Broyden's takes in function. Hey, just wanted to interject really quick and state that this whole section is just based off of a syntax error. Make sure that your parentheses are correct when you're inputting Broyden's method for approximating the Jacobian from Wikipedia. Okay, so that's what is all happening in this sped up clip. Let's stop that. We have a problem here. After x1, I'm not reevaluating f1. Okay, so this should always come in a pair. So let's try this again. There we go. Perfect. Just a little bit of bug fixing and we're there. Check that out. We have rather close values for convergence of an answer, and we're pretty close to zero. Here. Okay, so let's go off and talk about it. Let's leave you with some notes about Broyden. What you notice about Broyden is that this expensive inverse only happens once at the beginning and a couple times during the algorithm if we're not making good progress. So it resets itself if the Jacobian is becoming too corrupted. The guess and adjustment for the Jacobian is not good enough. Okay, and again, you notice how the next natural thing from root solving is minimization, maximization, right? Because you know from calculus 1 that the roots of the first derivative of a function is the critical values of said function. Okay, I believe that's all that's needed to be said about Broyden's method. Okay, so it's a little bit more involved, way more involved than Newton's method, but the main advantage is that we're avoiding this expensive inverse operator, allowing us to solve more complex equations of maybe hundreds of independent variables and hundreds of functions. So that will save a lot of time when compared to Newton's method. Okay, so that will conclude this video. Next video, we'll go off and show a proof for Broyden's method. Okay, see you in the next video. Okay, so welcome back to another video of computational methods. For today, we're going to be deriving Broyden's method. Okay, and recall that Broyden's method relies on this idea of iteratively improving the Jacobian based on an initial true Jacobian calculation. So you only calculate the Jacobian once, avoiding that expensive operation every iteration. Broyden's method's derivation, this one will rely on the idea of linearizing for an approximation of a function. Such that this function f of x may be approximated by the f of x at some value k, okay, plus an adjustment, and the adjustment consists of the Jacobian multiplied by an exploratory step. Sure, let's go off and think about Broyden's method. In Broyden's method, we approximate the Jacobian, so d, we'll call this d of k, equals the approximation to the true Jacobian. Okay, and for step k, that's going to equal the actual Jacobian. So we're root solving here, so we would like to find when the function is equal to 0, right? And this equals the f of x, again at some position k, plus the approximation of the Jacobian evaluated at f of x, evaluated at x at some position k, multiplied by, at this point I'll call this delta x, some exploratory step in the x direction. Okay, so let's say rather we have a delta x k plus 1. So we've moved a step and explored in a particular direction. Okay, and the linearization would say that, well, this new Jacobian is our unknown. It is our unknown, and we still have x evaluated, f of x evaluated at k, right? So this instead will equal the result of the exploratory step. So f of x k plus 1. Okay, the result of the exploratory steps, and we would like to solve for this new step. Okay, this new Jacobian approximation, and we go off and, well, we have two equations here, so we would like to gather it together, so I'll subtract upwards, and that's just convenient signage. Okay, that cancels out, and we're left with delta Jacobian approximation delta x, right? So, okay, let's say what if we have a exploratory step delta y, where delta y is perpendicular to delta, I don't know what the symbolism for perpendicular, let's do that, is perpendicular to delta x. Recall that if you look up here, based on these functions, the approximation to the Jacobian relies entirely on this exploratory step delta x, meaning it has absolutely no knowledge about or information about the exploratory step in the perpendicular direction. So what does that mean? If, for instance, delta y were 0, well, then delta d delta x equals, well, delta e delta, let's do y equals 0. But if delta y were to instead equal delta x by coincidence, well, then this delta d delta y equals f of x plus 1, k plus 1, right? So Broyden looks at this and thinks, okay, I want to gather this in one mathematical expression. I don't like this conditional we have here. It makes it rather complicated and not nice to look at. And he comes up with this. He comes up with some function g. Okay, let's say some function g. It will equal delta y, if I recall correctly, delta y dot product delta x over delta x dot product delta x multiplied by f of x k plus 1. Okay, wonderful. I had to stop and think, slow down and remember that. And this is wonderful. It's a wonderful mathematical expression. Why? Because if delta y were to be 0, then this whole thing goes to 0. Makes sense. If delta y were to be delta x, well, then this equals 1. And we have f of x k plus 1. Wonderful. Okay? But we don't... This isn't quite matching... This isn't quite matching the Broyden's method yet. So we're going to have to manipulate our equation a bit. And the first manipulation that Broyden thinks of to make this a little nicer is that, well, matrix multiplication looks a little nicer than dot products, right? So then that we have to start thinking about what exactly is delta y delta x. Recall that they're exploratory steps, but because we have vector functions, they are column vectors. Okay, delta y delta x. If we were to take the transpose of delta x, then we get a row vector, okay? So we can rearrange it as such. If we were to take the transpose of delta x, we get delta, we can bring delta x in front there. No. We can instead replace this with delta y matrix multiplication delta x. Okay? And at this point, this dot product, I'm just going to represent it as the norm. Okay? We still have this f x k plus 1. So what now? We can move things around. Notice that delta x is over here. It's rather delta x transpose is over there. So we can start moving things around like such. Okay? This doesn't look quite right to me. It does not look quite right. I think I made a mistake somewhere. I think I made the mistake that I wasn't aware of my ordering. Because in order for matrix multiplication to equal the same thing, it has to be delta x transpose delta y. That's right, that's the ordering. And then we have x k plus 1. Okay, now I can move that there and there. Okay, so now I have f x evaluated at the new step k plus 1 multiplied by delta x transpose over the norm of delta x multiplied by delta y. So recall what this function even equals. What does this function even equals? This function is supposed to represent this up here, and it represents the change in the Jacobian multiplied by some exploratory step. In this case, in this context, it's y, right? So delta y. And that's rather convenient because then our delta y's cancel out. And let's move to a new page here. That's rather convenient, right? We'll move to a new page and our delta y is gone. And now what do we have? We have delta d being the approximation in Jacobian. So let's go ahead and expand that out to delta, the Jacobian at k plus 1 minus the Jacobian at k, right? So we can move that over. We can move this over to the other side and get it starting to look more like Broyden's notation. And it looks pretty close, but not exactly. What do we have here? We have f of x at k plus 1, but Broyden describes it in the change in delta x, change in delta f. change in f, that's redundant. Change in delta f is redundant. So what can we do here? Well, first things first, let's go ahead and change our d to j, just so we are matching Broyden's notation. In this case, I wanted to use d so that we to introduce it. I did not want you to be confused between the true Jacobian and the approximation, but to match Broyden, we'll start using j now. Okay. And the placement of things, I'll just start moving things around so that it starts looking like Broyden's method in his notation. So his notation has it looking a little something like this. Okay. And we have to use the well, what is delta x? What is delta f? Delta f is f evaluated at k plus 1 minus f evaluated at k. In other words, f x k plus 1 equals delta f plus f x at k. Right? Well, we'll use another idea. Well, first let's plug that in. So we have j k plus 1, the Jacobian at k approximation, and this delta f plus f of x k. Okay, matrix multiplied by the transpose of delta x over the norm of delta x. So not quite right. Doesn't look quite right. We're missing this Jacobian. Oops. We're missing this Jacobian here. And how do we get that? We go back to the idea of linearization, right? With the idea of linearization, we have this. We have this idea right here. That's what I'm looking for. We have this. We have the fact that we're root solving, so the 0 equals the approximation xk plus the approximation of the Jacobian at the first step multiplied by delta x. Right? So what do we have here? See the similarity? This is a pathway that we can use to substitute. So we go off and do it as such. We will have I'm not sure if this is the right path now that I'm thinking about it, but we'll go off and check it anyway. We'll check it out anyway. We will have negative delta x k equals, no, I believe that's equals Jacobian x evaluated at k delta x. Okay, so the negative would actually rather be here, so that when we plug it in, we plug this in right there. Well, this is starting to look more like Broyden's method. Okay, we lost faith a bit, but it ended up working out in the end. So what do we have? We have f delta f plus f x plus the, not even plus, minus the Jacobian, the previous Jacobian, times matrix multiplied by delta x over the norm of delta x, all matrix multiplied by the transpose. Hey, look at that. Look at that. We made it. That is exactly what you see on Wikipedia. You see? The notation is just different in the sense that I use n plus 1 and Broyden's or Wikipedia uses n minus 1, but hey, that is matching perfectly. And that's a rather quick derivation actually. Just a 2-pager. Not bad. Okay? So there you have it. There is the derivation of Broyden's method, and that will conclude this particular video series. Okay? So thank you, and I'll see you in the next video.